All right. Hello, I'm James Watson.
And I'm Siddhant Keshkar.
And today we'd like to talk to you about behavior trees, task failure identification, and how they relate to our work in robotic assembly. Now, the goal of industrial robotics is to be able to manufacture anything we can imagine. The manufacturing system should be programmable, it should be adaptable, it should be able to accomplish all industrial tasks. We can think of this as a level 5 industrial automated system, able to act on human goals without detailed instructions from humans themselves. We haven't achieved this, but we can think of as an inspirational example from pop culture, the complex industrial robot R2-D2. We have not, which is able to repair any starship in mid-flight using only the ship's blueprints. We're not quite there yet, but there's some development that has to take place.
So our field requires benchmarks to prove the state-of-the-art methods for industrial robotics. At IROS 2019, the American National Institute of Standards and Technology came up with a robotic assembly competition that had a task board benchmark, which included common assembly tasks such as the threaded fasteners, insertions, mesh gears, and cable routing. The task board problems include parallel, sequential, and hierarchical relationships between these individual assembly actions. The type and ordering of these actions are a representation of these activities that are planned and performed by the industrial assembly system. Our current system is designed to accomplish these tasks. So our system is based upon an array of movement and sensing and computational capabilities that are useful in assembly and general manipulation. So it consists of the Universal Robotics UR5 manipulator arm. Then we have an Optoforce 6-TOF force torque sensor that's attached between the UR5 wrist and the gripper. The gripper is the robotic material smart hand that is integrated with a real sense camera and a computation, and it has two independent impedance control fingers. The planning and control takes place on the NVIDIA Jetson, and the software is combined with the RM Studio libraries and integrated with Jupyter notebooks. So using this system, we tested the common assembly operations that was published in the work on Advanced Robotics 2020 special issue.
One of these algorithms was a spiral insertion algorithm, which we tested on one of the small pulleys on the task board. This algorithm proceeds in several steps. In the following steps, first we locate the wheel and a shaft. The wheel is grasped and moved above the shaft, moved down to contact, and then spiraled out in a slow outward spiral motion. Meanwhile, we're monitoring the wrist forces and torques for one of two stop conditions, which is a spike in lateral torque or a decrease in reaction force against the wrist, indicating an insertion. Next, we do a force-limited push, and finally, we do a tamp operation to relieve the wheel from binding. So we're also recording the forces and torques at the wrist with the intent of identifying qualitative features of success and failure. So we can see in the spiral operation, the X and Y forces are similar in magnitude and 90 degrees out of phase. And in a successful operation, we see that drop in Z force as the wheel engages the shaft. In failures, we observed failures that were due to tilting of the wheel as it was brought down on the shaft. And we saw this in the wrist forces as the wheel was partially engaged with the shaft with more freedom in one direction, in one axis, and less freedom in the other.
So we observed that spiral insert is better suited for a small diameter cylindrical insertion. But for a large diameter insertion, there's a simpler approach, which we call as the tilt insert. So we applied the tilt insert to the insertion of a large bearing, and it proceeds with the following steps. First, we locate the bearing and the hole. Then we grasp the bearing and move it above the hole. Then the bearing is tilted such that the lowest edge of the bearing is centered on the hole. This is because when the bearing is brought upright, the curvature of the hole tends to bring the bearing to its center. Hence, when the bearing is tilted to vertical, it's given a final push. If we see a binding, we apply a tamp operation. So with tilt insert, we try to identify features for successful and a failed operation. So looking at the force plots for the successful trial, we see that the reaction force against the wrist goes to 0 as it's relieved when the bearing enters the hole. Then the force away from the wrist increases as the bearing pulls back and it's bound to the hole in its return to vertical. Now, in the failed trial, the robot tries to tilt the bearing into the hole, but the bearing is not aligned properly. So this increases the force against the wrist. Now, looking at the torque plots, we see that for a successful trial, the torque across Y peaks and then falls. This is because the bearing resists being rotated within its hole and pops into place. So for the failed trial, we see that it lacks the falling edge of the TY peak. And this is because of the misalignment, and the torque is never relieved.
So we also tested the suitability of the gripper for making threaded connections because these are common to all manufactured products. Our algorithm is for attaching a nut to the stud and proceeds in the following steps. We find the position of the nut and the stud. We spiral the nut onto the stud, and then we perform a tightening loop that executes until a resistance torque is encountered, beginning with rotating 2 flats clockwise while descending with a pitch, opening the gripper, rotating back counterclockwise 2 flats, and then closing the gripper. So the forces seen during a threading operation follow a sawtooth profile. A successful attempt is distinguished by a descending staircase profile of increasing reaction force on the wrist due to base contact with the base plate. Failures only manifested themselves during the spiral insert phase. We didn't observe any cross-threading events, surprisingly enough. And so this force profile was similar to the force profile we saw in the pulley, the failed force profile of the pulley.
So we have been busy with our development since the work was presented on the 2020 Advanced Robotics Special issue. The results from there were highly based upon the system that was deployed for the World Robotics Summit 2018 Assembly Challenge. The robot's actions were largely hard-coded and the results were very unflexible. Hence, to reduce this amount of repeated code, we wrapped common actions into skilled functions. This looks straightforward at first, but with different failures, we added more and more condition checks and phases to our skill. But at competition time, we saw that our skill functions look like a hacked-together piece of finite state machine. We found that behavior trees are a favorable alternatives to these informal FSMs.
So why behavior trees? It's because industrial tasks are hierarchical in nature, being composed of subtasks and individual actions. So we believe that planning of industrial tasks should match this tree structure. And also the planner should be reactive, being able to deploy recovery actions in addition to, in response to failures at the subtask or the action level. Take, for example, the assembly tree at the right composed of subassemblies. So subtasks should tackle these subassemblies, and individual actions in our scheme should join individual parts. And should a subassembly fail, then replanning should occur at the subtask level. And our hope also is to be able to redeploy subplans for similar subassemblies that we see in the future. And so just a quick overview of how behavior trees are unique and flexible. So control is passed from the root of the tree to the leaves of the tree. And as each node is visited, the node is going to return running success or failure to its parent. And so in this scheme, the subtrees and the nodes are interchangeable, which makes behavior trees modular and composable. So this behavior tree shows as an example a behavior that's going to fetch a ball. So the root node is a sequence node that's going to visit each of its children in sequence until the sequence either succeeds or fails. The subtree on the left is for finding the ball. Its root is a selector node that's going to visit each of its children over and over until the subtree succeeds. So this subtree is going to continually check if it's near the ball, and if not, it's going to repeat the approach ball action until it is. And this makes the behavior tree reactive.
So in this slide, we have the spiral insert behavior tree from our experiment. At the top, we have a sequence node that records the force and the torque data during the spiral insert procedure. At the middle level, we have the satisfying preconditions for the spiral insert, like grasping the part and moving it to the insertion location. Now, at the deepest subtree, we have the actual spiral insert skill. So in our most recent experiment, we repeat the spiral insert and the tilt insert many times to achieve the goal of finding the features for a successful versus a failed attempt. We observed that the lighting conditions and the relative camera location changed the system estimate of the part positions by several millimeters. So in this experiment, we perturbed the grasp pose by several millimeters to see if we could detect insertion failures caused by this misalignment. So we ran across 450 trials for each of the two skills while collecting the force and torque data throughout the action via our wrist sensor. So the qualitative features that were presented in our previous experiment are not as evident as in this experiment. Here we see for the spiral insert, both the successes and the failures have a periodicity in the force and the torque plots. This indicates the spiral insert. And then in both the cases, the action terminates as the large spike due to the lateral torque condition. In the force plot, we see that there are no discernible differences, but except for length. So we see that for a failed attempt, the spiral insert goes on and misses the hole, goes much longer than a successful trial.
So we have similar plots for the tilt insert. For a successful operation, we see a large spike in reaction force against the wrist as the fingers strike either side of the hole. And this spike is less dramatic in the failed attempt. Also in the successful attempt, there is a large spike in torque around the wrist's own y-axis. And so these taken together make it easy to differentiate between success and failure in tilt insert. And we saw this when we tried to automatically differentiate success and failure using our neural network models, which we developed for that purpose. We deployed several models, beginning with the simplest multi-layer perceptron possible. We compared this to an example from the literature by Moreira et al. And we also modified this model with hopes of getting improved performance. So as you can see, all of these neural network models perform similarly, reasonably well, between 85 and 90% accuracy across trials. Spiral insert had slightly less accuracy, the greater spread. Actually, interestingly enough, Moreira performed slightly better than its own publication when applied to our problem, but our attempt at improving it didn't really result in better performance.
So we also looked at the machine learning models such as logistic regression, k-nearest neighbors, naive Bayes, support vector machines, random forest, and AdaBoost classifiers. We saw that the machine learning models perform surprisingly well and even better than the neural network models, with SVM and logistic regression performing the best out of the machine learning classifiers. But we want to spend more time tuning these and the NN models as well to ensure that we find the right tool for the job of failure identification. So our goal is to increase the success rate and decrease the execution time of the behavior trees that perform our assembly tasks. Now, in the initial results that we discussed today, that's just the beginning of our planned development into a flexible and reliable robotic assembly, which eventually leads to a fully autonomous manufacturing system. Our immediate goal here is to select a classification method that's appropriate for identifying failure in progress and hopes that it can be stopped in time to recover.
So also during the testing of these insertion skills, we hand labeled different failure modes that occurred during all these 450 trials. So we're going to be adding capability to our behavior tree to automatically differentiate between these different failure modes and choose the appropriate recovery action for each type of failure. Also in the medium term, we're going to be adding 3D pose estimation to our system, where in the past we're using 2D. Longer term, we'd like to automatically construct and manage multiple simultaneous plans and based on user-specified priorities, available resources, and the likelihood of success of each action in each plan. So we'd like to thank the National Science Foundation, NIST, and Robotic Materials for supporting our work. I'd like to thank you for listening to our talk. And at this time, we'd like to answer your question.
Thank you, James and Siddhant, very much. It's very, very informative. Your number of trials is very staggering, seeing 500 plus trials. That's very encouraging for statistical significance also.
Yeah, we were working hard to get as many trials as possible with limited access to our equipment.
Understood. Anybody have any questions for our speakers?
This is Joe. Hi, James. Nice to see you. And Siddhant, I haven't met you, but nice to meet you. I was wondering, I sort of had to step away for a second at the beginning of your talk. Did you talk about the Robotic Materials gripper platform that you're working with at all? Maybe you can give us a little overview.
Yeah, we did do a quick rundown.
Okay.
Let me go ahead and share my screen again. But we did have a nice cutaway view. Oh, hold on. We did have a nice cutaway view from the patent application about the gripper. And so if we have this, go back to our cutaway view here and move my zoom window out of the way. This is the view inside the gripper. So this is being mounted on a UR5 arm. We have a 6-dot force torque sensor. We have an NVIDIA Jetson on the undercarriage right here. We have an Intel RealSense 410 camera, I believe, a D410 camera. We have a couple of Dynamixel impedance controlled servos driving these independently controlled impedance controlled fingers. So that's kind of a quick rundown of the parts of this gripper that's mounted on the end of this UR5 robot.
Mm-hmm. Do you know if this gripper is commercially available now, or will it be for other researchers to do experimentation with it?
So yeah, it has been offered. It has been offered to other researchers in the past. I'm sure if you talk to, if you contact Robotic Materials, we can arrange possibly to get some additional grippers out there. So there's been a few orders in the past of these.
Great, thank you.
You're welcome. Any other questions?
Maybe I'll ask you, what do you see as kind of the biggest bottleneck for your machine learning solution. You had mentioned that the repositioning of the camera relative to the objects had very varied results. Is that maybe the biggest bottleneck there?
Probably. So I think, like I said, we're changing our vision strategy, because like before I think the bottleneck is we had to, like I said, sight in these parts, and then so that like there's advantage and disadvantage to having your camera on your arm, and so we're kind of lacking this overhead view with our from our parts, and then as soon as we sight that in and we bring the part in directly local to where we're working, then at that point we're relying on our force feedback. And so we're kind of going to be, we're going to be continuing to follow that strategy in that we sight in first, and we're going to be using our camera to get hopefully a better 3D pose to improve our grip on these items, and that's work that's just beginning. And we also probably another bottleneck is that we're hoping, but we haven't confirmed yet, that what we learn for these insertions aren't specific to, the mating of two specific parts. That the hope is that we find features that are transferable between all tilt operations or all spiral insertions, such that we're not having to, run 450 trials for each mating of each pairing of parts in an assembly. I hope I answered the question.
You did indeed, and that your last note there is also highly salient to another workshop that was held during RSS regarding generating different test methods and materials for evaluating machine learning for issues like transferability of capabilities and things like that. So that's it's an unfortunate problem, but I think this is more evidence as to why we need resources to support it.
We'll definitely have to take a look at that.
All right, thank you very much.